Here we have the second round of examples of volumes of solids of evolution, and these are going to include a bit of a new spin, which has to do with the fact that we may have regions that don't necessarily just butt right up against the axis of rotation the entire way. And our first example will involve the region bounded in the first quadrant by the line y equals 2x and the parabola y equals x squared. They, of course, are going to intersect at x equals 0, y equals 0, and at the point 2, 4. And if I rotate this thing around the x-axis, I am going to be in a bit of an interesting situation. If it had not been for this boundary here, if it had just been x equals 2, then we would have, of course, had a cone. But what's going to happen here is, because there's this sort of blank space in the region, there's going to end up being, when we rotate, an empty space inside the solid. So it's sort of going to be a cone with kind of a pointy hole drilled out of it, if you will. And so the question is, what does that empty space mean in terms of getting an answer to the volume question? Short answer is, you can just take the volume of the cone and subtract from it the volume of that empty space. And the way that usually is conceived of is to imagine slicing perpendicular to the axis of rotation, as we've been doing. But what you get then is not a solid circular disk, but you get a disk with sort of a concentric hole punched out of it. And these in the calculus trade are called washers. And so what we're going to do is just take the one volume minus the other. And the way this typically done is that we distribute out the pi, and then we just apply the integral to the one radius squared minus the other radius squared. And so this would be, in this case, since we're slicing horizontally using cross sections perpendicular to the x-axis, I guess that would be vertical slices. From 0 to 2, those will be the limits of our integral, and then it's going to be pi times the outer radius squared, and the outer radius in this case, the curve farthest from the axis of rotation, is y equals 2x, minus the inner radius squared, and in this case the inner radius squared is y equals x squared, because again it's closer to the axis of rotation. And so here is our integral. We just have to work it out. So it's pi integral 0 to 2 4x squared minus x to the fourth dx, which is going to be pi times the quantity, let's see, x 4/3 x cubed minus x to the fifth over 5 from 0 to 2, and we're going to have our pi, and then if I stick a 2 in here, I have 8 times the 4/3 is something like 32/3, and if I just cube the 5, I'm going to have 32 over the 5, and then of course if I plug a 0 in for x in both of those terms, I'll also get a 0, and if you do a little arithmetic, I claim you're going to come out with 64 pi over 15. Generically, if you were to try to make a formula for these volumes, what would they look like? Well, they would be integral from wherever to wherever, pi times the outer radius squared minus the inner radius squared dx, if we happen to be working with a situation where our slices are perpendicular to the x-axis due to a rotation around a horizontal line. As we'll see momentarily, though, it doesn't necessarily even have to be an axis, and so rather than write something like f of x or g of y or whatever the case may be, I encourage you to remember this and to think of this in terms of an outer radius and an inner radius, because that's generalizable to situations where it's a vertical axis of rotation, a horizontal axis of rotation, an axis of rotation that may not be either the x-axis or the y-axis. So as much as possible, train yourself to think of this as being the pattern, because otherwise you have to sort of memorize a bunch of different patterns, and I think it becomes a lot more difficult. All right. The climactic example. We have the region bounded by y equals x cubed, y equals 8, and the y-axis, but we're not going to rotate it around the x-axis or the y-axis. We're going to rotate it around the line x equals -1. I know. And so the first thing we have to do, just in terms of getting a picture, is to, probably the easiest thing to do is to reflect this region across that line, and then sort of do your little circular top and bottom-y thing. And so this is going to be some kind of a deal with a circle drilled out of it, basically, or a cylinder drilled out of it. And if we slice from the bottom to the top, we will get circular discs. And this would be one such disk, just for example. And so our task is to figure out what this volume is. And so it's going to be integral from, well, let's see, we're slicing in this fashion perpendicular to x equals 1, a -1, which would be the same as being perpendicular to the y-axis. And so we're going to integrate from the bottom to the top. That's 0 to 8. I didn't leave room for my pi, but there's a pi out in front. I didn't leave room for my pi. And then it's going to be the outer radius squared minus the inner radius squared. And you need to be fairly aware of what your grouping symbols are doing. And so what are the outer and the inner radius? And this is where it can get a little sneaky. Let's start with the easy one. The inner radius is 1, because it just runs from this inner boundary of the region to which is at x equals 0 to the axis of rotation at x equals -1, and so of course it's going to be 1. And I don't really sweat the issue of the subtraction. You know that the radius has to be positive, and so strictly speaking, I suppose I'm taking 0 minus -1 and getting 1, but as a practical matter, it's just that's how far apart these are. Now, the outer radius. This is the curve y equals x cubed, also known as x equals the cube root of y. And you might think, well, it's just the cube root of y, but no, because the outer radius runs, I should have a darker marker, the outer radius runs all the way from this curve not just to 0, but to x equals -1. And so it's that distance, the cube root of y, plus another 1. Or if you like, you can just imagine that you're subtracting these x coordinates directly, and so the x coordinate here in terms of y is going to be the cube root of y. The x coordinate here is going to be -1, and the cube root of y minus -1 is, of course, the cube root of y plus 1. Now, it's just on us to do the arithmetic right. So I'll take it the first few steps. I don't know that we need to take it all the way. If I square this thing out, I'm going to have something like y to the 2/3 plus y to the 1/3, 2y to the 1/3 plus 1, and then minus 1, and I guess I really don't need to separate those in any way, dy. And so the ones, of course, are going to cancel, and at this point it's just rational powers of the variable, and so I'll leave it to you to work that out for yourself.